Controllability is one descriptor of a system. This video goes over the definition of controllability, then examining the controllability of different systems. The last item to be developed is the controllability matrix, which provides a generalized means of assessing the controllability for a system. And the video concludes with an example. If an input to a system can be found that takes every state variable from a desired initial state to a desired final state, then the system is said to be controllable. Again, if there is some input that will take every state variable from its initial value to a final value, desired final value, then the system is said to be controllable. You can see the meaning of that in the idea that the input can guide the behavior of every state variable. So every state variable is controllable. The system is controllable. And one upshot of this is that if you can't control the behavior of a state variable, then you can't place all the closed loop poles. And so the pole placement method that we looked at earlier would not be valid for a system that's not controllable. Now, the input can influence a state variable either directly or through coupling of variables. So it's not always clear or easy to see whether or not a system is controllable. Let's look at some systems where it is easy to see controllability. First of all, we have the system with this diagonal state matrix and the input matrix B, which is made up of all ones. If we were to rewrite this as three separate equations, you can see pretty clearly that this system is controllable because the input drives all the state variables. U affects x1, U affects x2, and U affects x3. Now, here is a very similar system, same state matrix, but the input matrix has a 0 on the first row. And this gives us the three first-order differential equations shown here. And this system is not controllable, what's called uncontrollable, because x1 is not controlled by the input. So there's no way in this system for the input to affect x1. Now, for most systems, the state matrix isn't diagonal, and so the relationships between the input u and the state variables x sub I is not as clear as in the previous slide. What we want is a mean for testing general systems controllability, and we use the controllability matrix for that. Now we're talking about, in general, an nth order system. So we have a system with this state equation. This system is controllable if the matrix C sub m, which we'll call the controllability matrix, which is equal to b, a times b, a squared times b, all the way up to a n minus 1 times b. So this controllability matrix is a square matrix, and it has n rows and n columns. This system, this nth order system, is controllable if this matrix has full rank, if it's of rank n. So this provides a means of verifying the controllability of a system for any general system. Now we'll look at an example to close the video. Here we have a fourth order system, and we want to see whether or not it's controllable. We have these values for the spring constants and damping and masses. And so we'll choose the position and velocity of the two masses as our state variables, x1, v1, x2, v2. Here's the resulting state equation, and our state matrix is shown here, and our input matrix B. So we end up with a controllability matrix, which is b, ab, a squared b, a cubed b, that has these values. The rank of this matrix is 4. Therefore, this system is controllable. That means that there exists some force, that's a function of time, that can bring all the state variables, x1, v1, x2, v2, from any desired initial values to any desired final values. So the controllability of a system is an important aspect to consider when using state space control methods.